Now we are looking at what we can get from RRI after having imported the EP2 as a RRI object in the database. This object is stored under miscellaneous, and now to use RRI calculation, we double-click on the object, and we have a certain number of acoustic descriptors you can directly create from the RRI object. Or from top to bottom, you have the OP2 regarding the loaded phase. In that case, the loaded phase and the radiating phase are the same, but you can dissociate your calculation into two objects. One phase for applying the load, and one phase to radiate the energy in the receiver cavity if you have a box system with two plates strongly connected together. Here, a recall of the number of modes and the range of eigenvalues you have scanned. The damping loss factor is a user-defined spectrum you can change here for calculating all resonant values that depend on damping, such as the velocity. This is the wave number of the panel. It is the analytical wave number. I will select it here because we need to compute the added fluid mass, and then for that we need this wave number that have been created from an equivalent analytical SCA plate. Here the calculation frequency that is performed in narrow band per hertz, in that case 1 hertz up to 8 kilohertz, and when the spectrum has been computed up to 8 kilo, we can interpolate or integrate into constant octave and 1/3 octave, the same band then available in C+, down to 1/24 octave, in order that you can compute this parameter with the same frequency band you use in the SAM model. So you can import them without any interpolation in that case. The integration between done from a narrow band. You can increase the resolution if you like. When I'm computing the RRI, so I do a modal summation, including the radiation efficiency, as shown in the theory. And then you have all these parameters you can directly now plot. Transmission loss coefficient, they are decomposed into total transmission coefficient. And for those who are more or less accustomed to transmission loss in dB, you have this 30 dB up to 40 dB attenuation of the power radiated through the plate. So it's better for comparison to use transmission coefficient, because higher it is, higher is the transmission. Then you have also the non-resonant and resonant transmission. In that case, you see the non-resonant transmission is below the resonant frequency, and when you have no mode in a band, there is no, per definition, no resonant energy in this band, and the result is zero in that case, because we put all the resonant energy in the band where are the related modes. If you look at total, then it will give you the interpolation, the right result from the modal summation. Which is an envelope of both transmission. Oh, we have, of course, radiation efficiency. We have two different plots. One is the modal radiation efficiency. That means each mode at its resonance frequency radiates energy, so it's a peak. The second is each in a band, the radiation is average of the modal radiation efficiency computed from the RRI radiation efficiency tab. And the results in that case are not too different. Third is the velocity, resonant and total velocity. And the CLF, which is in fact normalized spectrum of radiation efficiency, which is given here. Then directly usable to replace an acoustic to structure CLF in the calculation. Obviously the mass also, which is computed from the mode, constant in that case because it's an homogeneous plate. And the mode count, which is computed from the FEM modal series. And that can be obviously compared to the analytical calculation, because we have only one subsystem in that case to model the plate. Okay, so you see it's really easy to use. A few parameters. Don't forget the wave number is used, or the structure is used for computing the added mass, and also to take into account correction in a free condition. That means when your system is excited both sides, it's like a plate suspended in a reverberant chamber and excited both sides, so there is some diffraction both sides, and this is taken into account thanks to the structural wave number. And generally what we do in that case is to use the structural wave number. So there is we created one from the geometry file of the finite element model. And when I graph, I adjust this wave number. And if I need it for RRI, I can just store it in the database under wave number for RRI. Okay, save. Now, if I come back to my RRI database, when I open, I can select this one if I like. So you can also, if you have a virtual model, generally the VSC model is also delivering a wave number, numerical wave number, and you can use it also in place of the analytical wave number. So you can have all your data computed from the finite element model in that case. Okay, so this is the first view on how to use RRI, and I close this session.